Good morning, and thanks for joining our session. We'll start by a brief overview of DevSentient and the problem we're solving in our product, and then we'll transition to show you a few cool demos of some of the projects and solutions that can be built on the Hyperplane platform. So I'll start. So my name is Evgeny Valis. I'm one of the co-founders of DevSentient. And we started DevSentient originally for a completely different purpose. But as we were building a different product, a different software really, we realized, and I think this won't be news to anyone here at this conference, that there is a gap. There's a gap in terms of the ability of science teams that are kind of trying to get an idea up and running, so to go from idea to something that's generating value and it's being used. There's a gap in that process, right? There's really good tools out there, and yet it's still not something that is smooth and streamlined. And so we've built Hyperplane. So Hyperplane is our platform, and we'll talk a lot about it. But let me just open up by looking at some of the pain points that led to the creation of Hyperplane. So I don't think anyone in this event will disagree with the quotes that we have here on the slide. And while the quotes are not attributed to specific individuals, these are all real pain points that chief data and analytics officers, CIOs, CTOs, chief data scientists experience on a daily basis. And so really what it all comes down to is the ability of scientists to get their work into production. So how do you actually operationalize scientific work that has proven to have good merit? And the space itself is massive. I mean, every company out there knows that the future of software is in leveraging data both for decision making, for alerting, monitoring. Software is no longer just a rule-based kind of set of libraries. Everything that's being developed, especially at large scale, has to leverage data and has to leverage insights from that data. And so the spend on data science across all industries is growing rapidly, growing exponentially. But what we're not seeing, or we're seeing very little of, is actual ROI, actual new revenue, actual cost savings that have been realized and materialized in the balance sheets of the companies that make these investments. And while some of these stats are obviously evolving and it's a point in time snapshot, the entire team at DevSentient has been working in the AI space for quite some time. And one thing that I think we all agree on, and we've all experienced personally, is that there is indeed a very large drop-off between the POC stage of data science and machine learning work and what happens after that, which is scaling, automation, productionization, and so on. And so that's the opportunity that we're tapping into, and that's the opportunity we want to create for DevSentient's clients. So what is Hyperplane actually? What does the platform do? The platform is designed as an end-to-end workflow solution. It's not designed to solve only one step in that process, and it's not designed to reinvent the wheel in any way. What Hyperplane does is it ties together the best tools the best point solutions out there, and the best open source and commercial products that can solve specific steps in that workflow of data science. And it creates the path for scientists to go from beginning to end entirely in a self-sufficient way, without requiring engineering support or IT support, without requiring data engineers, really being able to get all the way to full implementation in an entirely independent way. So there's a number of kind of key aspects of this process that we had to tackle, and we had to put kind of all of our energy to to enable our clients to do efficiently. So the first thing is scale, right? So if you think about scale in data science, that's usually one of the biggest hurdles. So let's say you start with a small data set and you've proven that you can get some really good results with it. You can train a model, the model is performant, and it's potentially can produce a big lift for the business. But going from that small scale experimentation with a small data set to processing terabytes or petabytes of data with SLAs, with time constraints, and with kind of production requirements, there's a very long journey to achieve that. And so what Hyperplane does is it enables scientists to go from small scale experimentation to essentially unlimited size data with a single line of code. And I know it sounds magical, but we'll show you exactly how it works. The second thing is deployment, automation, monitoring, and alerting. So once you have a working solution, everything that solution does needs to be run automatically, right? Scientists typically work in a Jupyter environment or another notebook environment, and they want to run their code automatically once they think it's ready. So we facilitate that process, and we actually make it extremely easy to take scientific code, notebook-based code, and convert it into services, pipelines, and functions that can be triggered programmatically or run on a schedule. And then the last but not least portion of the process is once you're live in production, someone has to maintain that solution. And it can't be the DevOps engineer that wakes up at 2 a.m. in the morning and fixes, your neural network or your XGBoost model. And it can't be a scientist who wakes up at 2 a.m. in the morning and starts resolving network permissions issues and routing issues. You really need to be able to handle the entire end-to-end aspect of the solution in real time, quickly, and you need both the scientific component and the engineering component. And so what we've done with Hyperplane is we've created a mechanism for engineers and scientists to quickly tackle production issues without having to deal with environment differences, communication differences, terminology. Both the engineers and the scientists know exactly what failed, know exactly how to reproduce it, and how to fix and redeploy. And so, to summarize the differences of using Hyperplane compared to pretty much anything else out there, you scale up with a single line of code. So there's no engineering effort involved in taking a small scale computation and running it at a massive scale in the vast majority of cases. Of course, this can never be 100% true. There's cases where you would need to do some extra work, but by and large, and this is based on the clients of DevSentient, by and large, most machine learning code can be scaled up with a single line of code and very little effort. We support deployment of Jupyter notebooks directly, turning notebooks into functions, into pipelines, into scheduled jobs. Everything can be done through the notebook, so scientists never have to migrate their notebook-based code into Python modules or any other kind of modules. There's no need to create containers, to write Docker files. None of that is required. You can essentially do all of your implementation work in a Jupyter notebook and then have it deployed and run and doing all of these different things. And again, we'll show you exactly how that works. We built this originally with significant consideration to cost savings on infrastructure. And so one of the things that Hyperplane does is it makes it reliable to use spot infrastructure or preemptible infrastructure, depending on your cloud provider, for a vast majority of data science and ETL jobs. And so what that means is that you can reliably run most of your workloads while saving about 80% of the infrastructure cost. Right? Because if you think about a pipeline that's processing, let's say, 20 terabytes of data every 5 minutes, and there's actually one company using Hyperplane exactly this way, when you're processing that much data that frequently, being able to do that on spot infrastructure saves you very significant amounts of infrastructure spent per year. Philosophically, we're opposed to vendor lock-in. We've experienced that pain ourselves in our various past experiences, and so we've built Hyperplane to be easy to deploy, easy to integrate. It takes very little time to deploy into any infrastructure, whether cloud or on-prem. And there's no lock-in. You can drop in your existing code into the platform and start using all this functionality that I just described without any re-implementation. Of course, you could always move off of the platform if you choose to, but we hope that you won't, because it actually gives you a lot of useful functionality that you want to use, as opposed to forcing scientists to re-implement their solutions. And so the time to get up and running and the time to get value is extremely short, can be a matter of days or even hours in some cases. And then, the kind of, to wrap all of this up, the maintainability of the work is key. So the entire solution wouldn't really give any business value if scientists weren't able to then deploy their work and maintain it and be the owners of their work in production. And so we provide functionality to make that easy, seamless, to remove the need for scientists to become DevOps engineers and just let them be scientists, but be able to take on an operational role in that context. And so the end result is that companies and individuals who use Hyperplane go from idea to production very quickly. In some cases, before using Hyperplane, they were struggling for months. And once they deployed and kind of understood how to use it, which takes maybe a day or two, they were able to deploy solutions literally within days and actually have them running in production, processing large amounts of data and delivering business value. And so with that, I'll wrap up and I'll hand it over to Will from DevSentient, who is going to present a couple of demos.
Great, thanks, Evgeny. Let me just get my screen going here.
Will, we can't hear you.
Can you hear me now?
At least I can't hear you.
Okay, great. All right, so let's take a look at what the Hyperplane platform actually looks like. We'll start here at the login page. We'll see here that Hyperplane actually supports many different single sign-on providers. The deployment that I have right now has Google set up. And so I'm going to log into my Hyperplane dashboard using my Google single sign-on provider. And what you'll see here is the Hyperplane dashboard overview page. And as a user, when I log in, the first thing that I'm going to see up top here is a number of different applications. So there's the Jupyter server, which most of our data science users are familiar with. We have something called a GraphQL playground. So GraphQL is an API. It's similar to RESTful APIs. Sorry, it's different than RESTful APIs. It's a little more user-friendly. And so using the GraphQL playground, you can develop your APIs that can be used to programmatically run jobs or pipelines. And you can invoke these API calls as well through the playground. Thirdly, we have the Grafana dashboard. So this allows you to monitor various metrics related to your jobs or pipelines, things like CPU usage, memory, network bandwidth, those types of things. And then lastly, we have ML flow integration. So this allows your data scientists or your other users to save model metrics and version experiments and those types of things. And then lastly, below here, we just have a recent jobs pane, and this just displays the recent activity on the cluster, various different jobs and pipelines and what their status is. So let's walk through the workflow of how a data scientist would use this platform. Usually when I log in, the first thing that I'm going to do is go to my Jupyter server. And you'll notice here that there are a number of different options. So at DevSentient, we've built a number of different Docker images to help you get started quickly for a number of different data science use cases. So we have our stable image here, which contains a number of different data science packages. We have a deep learning specific image that contains PyTorch, MXNet, transformers for deep learning workloads. One of our clients works with climate related data. So we have an image here that contains all the different climate related packages. We have our GPU image that comes with GPU support and various GPU accelerated libraries like NVIDIA Rapids and GPU support for deep learning frameworks like PyTorch. And then two other images we have here related to running workloads such as SAS on Jupyter or R on Jupyter. And so what I'm going to do is I'm going to select my GPU image here, and I'm going to spin up a Jupyter hub. And this will just take a minute or so here as it's spinning up the Jupyter Hub server. And then I'll be able to see my Jupyter instance. All right. So here we go, it's spun up here. And if you used Jupyter Notebooks before or Jupyter Lab, you should be pretty familiar with this interface. Over on the left here, we have a user-mounted file system where users can download files or download Git repositories to work with. And then over here on the right, we have the main Jupyter Notebook interface where I have a couple notebooks and some files open that I'm going to walk through. So I'm going to start with this getting started notebook here. And the point of this notebook is to show you how straightforward it is to start up a Dask cluster on Hyperplane, and specifically a Dask cluster that has GPU support. So we'll be able to run some Rapids examples on Dask in a distributed fashion. So first what I'm going to do is I'm going to import some standard libraries here. One of the ones that I'm importing here is called Hyperplane. So this is our Hyperplane Python package that contains a number of different utilities to easily get up and running. And one of those is this initialize cluster here. So this is going to initialize a Dask cluster. And there's a number of different options that you can pass in related to processes, threads, the amount of memory or CPU cores that you'd like, the amount of workers in the cluster, number of GPUs, those sorts of things. Even something here called scheduler deploy mode. Scheduler deploy mode refers to either local, so it's running on this image, or it can be remote. And the reason why we give you that option is if you're running large jobs, Dask, the way it works is it maintains a computational graph of your various different operations. And if you're running a big job, this can get quite large and use up memory in order to manage. And so you can offload that scheduler to a remote pod. And one thing, as Evgeny mentioned, one of our philosophies is to have these short-lived tailored clusters. And so by having this here, I can spin up a cluster that is tailored towards my job, and I'm making sure that the infrastructure spend that I'm doing is one that's tailored towards my job. You'll notice here that the Hyperplane library also spins up the Dask dashboard as well for you and exposes a URL. So we can go to the Dask dashboard here as well. Not much is going on here yet, as we haven't run any computations, but you can see we have a GPU attached and it's using a little bit of memory here. So let's switch back and I'll run through the rest of my example. I'm going to import the Dask distributed library so I can interact with the cluster. And here I'm going to import the Dask cuDF library. So this is a NVIDIA Rapids library. And if you're familiar with the Dask data frame, this has a very similar API. The Dask CUDA data frame is a Dask data frame that can run on the GPU. So I'm going to import that library, and I'm just going to read in some flight-related data. And you can see here I'm using Dask cuDF to do that, so I'm reading the data straight into the GPU. And if we switch back over here to our GPU profile, oops, just trigger it. If we switch back over here to our GPU profile, you'll see, okay, we have some GPU utilization. The amount of memory that is being used on the GPU is increasing as we're reading in that data set. And
so,
I'm just...
Well, just a quick comment before you move on. I just want to add one more sentence about the ephemeral cluster. So it may kind of seem natural to do, but it makes a huge difference in terms of isolation, customizability, and just general convenience of using something like Dask or Spark. Right? So when you have a cluster that exists within the notebook and serves just one purpose, it's just there to perform that one calculation that Will is doing right now, you can configure it exactly as you see fit. You may need more memory or GPUs or CPUs. You may want to use threads versus processes. And all of that is configurable by the one scientist who's working on the notebook for the purpose of this calculation. And then you'll soon see what happens at the end of it. You kind of just tear it down and throw it away. And the benefit is that you have full isolation from any other workloads, any other jobs running. And then you can just do the same exact thing in production, so that each job has a tailored cluster that exists purely for the purpose of completing that job. And then that infrastructure gets released back once the job is done. Sorry, Will, back to you.
Thanks, Evgeny. So here I'm just going to run a simple group by operation. In my flight data, I want to see for each flight carrier and for each flight number within that flight carrier, what is the average distance that a specific flight number travels? So I'm going to run that, and because Dask is lazily evaluated, I'll have to call this compute function here. We'll switch back to our Dask dashboard, and you can see that there's some GPU utilization here, and the GPU memory is increasing. If we go to our status page, we can look at the task stream here as this is progressing. And I have my results here. And then last but not least, we have this cluster.close function. So this will tear down your cluster and send resources back to the pool when it's done. However, not to worry if you forget to include this, or if you forget to invoke the cluster.close function. We've implemented some smart garbage collection in the back end. Job is no longer running, or your Jupyter kernel is no longer running. We can easily garbage collect the cluster so that you are not spending additional money on infrastructure spend for resources that you're not using. Second demo I'm going to show is related to running something which is called TSNE. So TSNE is a dimensionality reduction technique, and it's particularly well suited for visualizing high dimensional data sets. I'm going to show you how fast it is to run this on the GPU. And when it comes to hyperplane, and more generally in GPU accelerated workloads, One thing that users do is, for example, if we consider the Rapids Docker image, the Rapids Docker image is pretty huge. It's about 15 gigabytes. And most of that image contains the NVIDIA Rapids library. And so pulling this down over a network or loading this into the Docker daemon can take quite an amount of time and really affects the user experience. So one thing that we've done in Hyperplane is we've done some interesting optimizations so that you can work with large libraries like these GPU accelerated libraries without having to have that user experience of really waiting a long time for these images and libraries to be initialized. And so I'll show you how easy it is to get started, once again, using a GPU accelerated library on Hyperplane. So I'm going to import these common libraries again. And you'll notice here that I'm going to read in some crypto trading data. And here I have a variable called symbol, and I want to read in some Bitcoin data. So I'm going to go ahead and I'm going to read that in. And I'm not going to run this on the CPU because we'll be sitting here waiting for more than 5 minutes. But I'll run this on the GPU just to show you that it is relatively quick. And for those that do not know, TSNE is a computationally intensive workload. And you can see that if you end up running it on a CPU, as it takes quite a lot of time. So that's going to run, and we see it completed in about 20 seconds or so. And we visualize it here, down here. But what if I want to run this more programmatically? Maybe I don't want to step through and run all these cells. I want a way of running this in a pipeline or a job or invoking it via an API. How can I go about doing that? So the way to do that is by creating a simple YAML file. And I'll switch over here. And this is what's called a pipeline YAML file. So I have a name here for my pipeline. The job type, it's a GPU related job, so it's going to run on that GPU image that we've made. And here's a list of the steps in the pipeline. I just have one step here, which is to run my TSNE Rapids demo. And the one nice thing about Hyperplane is that for your jobs and your pipelines, we save the fully executed notebook to your object storage solution of choice. And what this really allows for is increased auditability, as well as a really easy way of debugging these automated pipelines. And I'm going to show you a little later how we go about doing that. So once I have this pipeline YAML set up, I'll switch back here. And maybe, for example, for this type of pipeline, we see this symbol here set to Bitcoin. But maybe I also want to run this job on some other data. Maybe I have some Ethereum crypto trading data or some Dogecoin data, and I want to see what the visualization looks like for that particular symbol. Right now, this variable and this Bitcoin value are hard-coded, but we can actually change variables in our notebook to parameters. And the way we do this is we go to our property inspector over here, and we can mark a cell as a parameter cell. And this allows us to programmatically override variables in the notebook. So how do we go about doing this? I'll switch back to the Hyperplane overview page, and I'll go to my jobs tab here, and I'm going to create a new job. There's a number of different fields that I can select. So this is a GPU related job. There's some fields related to timeouts or retries in case of failure. And then I'm going to enter in the path here to my YAML file. You'll notice here on the left that it also builds up a GraphQL query. So if you didn't want to submit the job via the UI, you could submit this query via a GraphQL client or hand it to downstream engineering teams to integrate into product. And then when I mentioned the parameter cell, this is where we can override those values. So I'm going to say symbol. I'm going to kick off my first job with Bitcoin related data. And that's going to create the job. We can see now that job is pending here. And then I'm going to kick off a second job as well, but this one using Doge. And I know that I actually don't have Dogecoin data stored in my bucket, so this is actually going to error out. Okay, so let's take a look. All right, so these are in progress here, and they'll go ahead and run. But what I'll show you, and this will take about a minute or so, but what I'll show you in the meantime is I ran a job previously that failed due to the same reason. I wanted to load in Dogecoin and I didn't have it. And so I'll show you, I'll pull that data down so you can see how easy it is to debug. One thing you'll note here is, as I mentioned, we save that output notebook path, and this will show up here when that becomes available, and then we can easily just click the link and pull down that information. So let's see here. I'm going to click on the failed jobs selector up here so I can get an idea of the failed jobs that are happening. And I'm just going to copy that over. I'm going to go back to my Jupyter Lab here. I can open a terminal. And I have this stored in Google Cloud Storage. So I'm going to use the dhutil to pull this down. And it's going to pull down that notebook run. This is, as I said, the TSNE Rapids demo. And I can go back into my user-mounted file system here, and I see, okay, this is the job ID, and this is the output of my TSNE Rapids notebook. We see, okay, an exception was thrown. Let's take a look and see what exactly was the case. Okay, it looks like here I don't actually have Dogecoin data in my bucket, so that's why it failed. And that's pretty much it in terms of getting up and running on Hyperplane, how easy it is to spin up a cluster, to work with advanced GPU accelerated libraries like NVIDIA Rapids, and how to easily automate and submit these notebooks as jobs via either our UI or via an API call. So next, what I'm going to do is I'm going to turn it over to Christine, who is going to show you how to run a service in Hyperplane.
Okay, thanks, Will. So as Will said, Will has shown how to trigger a pipeline or a series of notebooks to run end-to-end, or even as a function with some parameters that you can change, either programmatically or through our dashboard itself. But now I want to show the workflow for when we don't actually want to run the pipelines end-to-end or steps of notebooks end-to-end, but instead we actually want our notebooks or code or even a dashboard, a simple dashboard application to run in an endless loop. So for this example, we'll just show a simple crypto trading bot that we've built. And instead of focusing on the details and the logic of the bot itself, I'd actually like to highlight some of the important cells. So of course, we can run this notebook like normal, just in our local Jupyter Hub cluster, or on our Hyperplane Jupyter Hub cluster. But the cell that I wanted to highlight is actually this one. The intention of this is to essentially run in an infinite loop of pulling some data, doing some pre-processing, applying some logic, and then doing the actual trades. So of course, we can run this entire notebook on our Hyperplane Jupyter Hub cluster, and we could just keep this notebook up and it'll be running. But if we can actually trigger this to run in a similar way to how we were running pipeline jobs before on Hyperplane, we can actually run this in a continuous loop without having to keep our cluster up or our notebook running, and we can use this for something else. So in contrast to the batch jobs or the series of steps that run end-to-end like Will showed earlier, we actually use these never-ending notebooks or scripts that you have as services. And as we can see later on, these services can run either as a never-ending pipeline that can be exposed in Hyperplane, and also to other teams in your organization if you choose. So once we have this notebook that runs, we can actually convert it to a service in Hyperplane in a process that's very similar to creating a pipeline job, which is really primarily 2 steps. So first, we just have to create our, so first we go to our folder and create our YAML. And this YAML, similar to what Will showed before, just shows the steps. And in this case, we just have the 1 step, which is our CryptoBot notebook, and we can specify our output path if there are any errors. And then after we save this and commit it to our repository, that's our first step, we can then go to our dashboard and then actually run it as a service. So in our dashboard, we can see the services page, whereas previously we were on the jobs page. You'll notice it's quite similar. The only real difference is the service page only shows the never-ending jobs that we have in progress. So you can already see we have a couple of these running. But to create a new service, all we do is simply press the plus button. And one thing to note here is that the timeout and the active timeout is set to -1, which indicates to Hyperplane that this is intended to be a never-ending job that just doesn't have a specified timeout. In this case, we should copy our YAML path as normal. So we copy our YAML path. Here, I just want to save the out file to clogs.csv, and then we can press create. And that's it. So at this point, Hyperplane will pick up the job and do some auto scaling to get it up and running. But in a couple of minutes, it'll change to in progress, and then our CryptoBot would be up and running in the background. So that was a very simple process of just changing a notebook and really just getting it into a service. But now that we have this, what if we wanted to take it a step further and actually visualize some of our bot's trades? So our currently running CryptoBot is just running at the back, saving the results to that out file that I specified and saving it in a cloud storage bucket. Now, what if we wanted to set up a very simple application to sort of pull that data that our bot is outputting and actually display it in a front end? So for this example, we just have a simple Flask application, but of course, you can use any other framework that you like Fast API, Django, anything else you'd like as well. And to get this dashboard running, so you can see it's a very minimal set. It's just the app file itself. To get this, once we know that our app is running, to get this running as a service again, so that we don't have to keep our JHub instances up, we just simply have to create a YAML. So in this YAML, we actually specify the set of instructions that gets the Flask application up and running. In this case, it's really just getting the this line which gets the app up and running. So same deal, we just have to save this and then commit it to our repository, and then we're done our first step. In the second step, we can go back to our services page and then actually get this job running. Again, the timeouts are set to -1, and I will need my YAML path. Let's copy that. And I want to read from the file clogs. So in this case, there's one difference because we want to display this as a dashboard in the front end, we want to display this front end on our dashboard. We just have to expose a port or specify an exposed port, which tells Hyperplane that we actually want to be able to see this. And I'll show what happens later. So we just press create. And we can see we successfully created a new service. So once we press create, Hyperplane will actually auto-scale the infrastructure to get the dashboards up. It depends on the cloud provider, so it can take a couple minutes. But I wanted to show what happens when you specify an exposed port. So as you can see, for the jobs that have an exposed port, we actually have a dashboard URL. So if we click that, we can actually visualize the dashboard that we put together earlier. In this case, it's just a simple, it's just a simple graph that shows the ADA over BTC price, as well as whenever there are buy or sell events, which will be marked in blue and red. So I think our bot hasn't made any trades in the past 5 minutes, but once that actually happens, we'll be able to visualize it. Again, the point of this isn't to show that we've created a very cool crypto bot or that we've created this dashboard specifically, but that it's very easy for machine learning scientists to expose an API endpoint that can be accessed by other teams or even display a dashboard. And they can really just do this from within the JHubs and within a notebook and then spin up a service and get something up and running very quickly. And of course, the workflow of sort of productionizing or deploying notebooks might be a little bit scary because your notebook can have errors. But as we showed earlier, we can actually make it very easy for the scientists to do the debugging and then redeploy the changes and sort of iterate very quickly with a continuous delivery mindset. And so that's it. I mean, we've seen how to simply run our code on Hyperplane, trigger the pipelines or a series of notebooks to run either on a schedule or even as a function with some parameters that we specify. And then also how we can run our code as a never-ending service or set up a dashboard very easily all through Hyperplane and in a very similar process. So at this point, I guess we like to take any questions about DevSentient or Hyperplane, or even, just the usage or some of the tech behind this.
Thanks, Christine. And while we wait to see if there's any questions, I think if Emil is still here, my understanding is we can actually do another run of this presentation for the folks that that may be joining from other sessions. Is that correct? Yep. All right, great. I see a question from Arthur. Not sure it was asked, how do you scale this service to support say, 1,000 TPS? So our platform, it's a great question. Right? So our platform is built on Kubernetes, and it can run whenever Kubernetes can run. So, if you're on the cloud, the way we scale really is we leverage extensively the Kubernetes mechanisms for auto-scaling, as well as the underlying cloud auto-scaling mechanisms. Where a lot of the work that Hyperplane does comes in is really the management of the resources, right? So let's say, you've scaled up a cluster of 100 nodes, a few thousand cores, a few terabytes of RAM, you've done a calculation, and now you need the resources for something else. We will handle that transition very quickly. So tearing down clusters, scaling up a different kind of cluster. And we handle the auto scaling all in a kind of a seamless way. So the users of the platform don't really need to think about it. It's all done underneath by the Hyperplane APIs. As an example, one of our clients uses Hyperplane to process clickstream data, and so they're channeling website clickstream data from major retailers all around the world, and it's terabytes of data every 5 minutes, and the jobs run on a 5-minute SLA. So there's a certain amount of resources that's just always on because it's constantly processing. But if there's a burst, the platform will just scale up additional resources to meet the demand. And I see you've asked to use regular Kubernetes or tailored something more specific. So we use Kubernetes, but we don't use anything that wouldn't work on OpenShift. And a lot of functionality we've implemented ourselves. We use Kubernetes kind of for the things it's really good at, right? So like abstracting away the exact cloud infrastructure, for example, managing deployments and kind of networking between pods and stuff like that. All of that is done by Kubernetes, but we can deploy just as easily on OpenShift, and it will work exactly the same way. Cool. Thanks, Arthur, for the question. Any other questions from the audience? All right, let's just give people a few more seconds, and then we'll do another run of the presentation in case folks are joining from other sessions. Yeah, I'll just write the same thing in the chat. All right, so we'll just give people a few minutes if they're looking to join from other sessions. This is the end of the demo. We're going to do another run of it in a couple of minutes. So for those who joined us for the first run, thank you, and feel free to reach out anytime. And we'll start another round of this in a couple of minutes. So we'll get started again. The second time we're doing this presentation this morning. So if you've seen the first one, the second this one will be more or less the same, as much as we can make it the same. And so this is for folks who are attending other sessions and might be interested in what DevSentient has to say. So I'll kick it off. We'll start with an overview of DevSentient, the company, and what we do, and then I'll transition it very quickly to Will and Christine, who will show demos of different aspects and workflows on the platform. So just to get things started, clearly the machine learning space is large, and it's something that we're all passionate about. But it's also a space that's still in a kind of an early stage of maturity. And you can see that, and you can hear that from executives across all industries who are responsible for getting data science and machine learning into operations and generating P&L based on the spending that they're incurring on their data science and machine learning teams. And so, some of the quotes that you see here, while we're not attributing them to specific people, I think we can all agree that these are all real challenges, and most chief data officers, chief analytics officers, CIOs, CTOs, chief data scientists would agree that generally speaking, scientists are great at experimentations. They're great at generating amazing POCs that prove that machine learning and data science can do great things for their company. Where a lot of the challenges is going from that experimentation phase all the way to production, all the way to deployment, and being able to support the work once it's deployed. And so that is the problem that we've set out to solve. So if you think about the industry overall, I think all companies in every industry, or at least I would struggle to find someone who would say that machine learning and data science is not important. Every company is investing in it. The investments are significant. The skill sets are expensive and scarce. And so the teams exist, the ideas are flowing, but a very large fraction of the ideas drop off and never make it to the product, never actually benefit the customer. And so the DevSentient team, all of us have been in the AI space for quite some time. And we've all personally experienced this, where an AI team is all set up, ready to go, produces some great POCs, and then struggles to get these POCs into production. And while the numbers of, the percentage of POCs that never materialize may not be exactly 87%, I mean, it's just a point in time snapshot that somebody produced. I think we're all pretty confident that the numbers are very high. The number of POCs that get thrown away and essentially never materialize, never convert to any new revenue or cost savings is extremely high. And so we're tapping into that, and we're unlocking that opportunity for our clients. So what is DevSentient and what is Hyperplane? Hyperplane is our end-to-end platform that is designed to get scientists from idea to production and to maintain their own work in an entirely self-sufficient way. So what we're trying to do is not provide another point solution, or is not to provide another entire kind of cloud ecosystem. We're solely focused on the workflow. We're solely focused on the workflow of the scientists as they go through the process of ideation, experimentation, scaling, automation, and then monitoring and issue resolution. And so the very first thing that scientists notice when they start using Hyperplane is how easy it is to scale their work. So typically, a data scientist would develop a solution or develop a proof of concept on top of a sample data set that they've pulled to their local environment, or potentially a cloud environment where they operate. And they'll usually restrict themselves for two reasons. One is pulling a lot of data is hard and potentially expensive, requires approvals. The second reason is they're limited by the infrastructure that they're on. So while they may be able to get sizable kind of compute instances, if you're operating at a truly large scale, you usually can't get enough of an instance or enough of a memory or CPU capacity in one computer, in one instance, to be able to handle data at full scale. And so when scientists start using Hyperplane, the experience that they have is that they can take their existing Jupyter notebooks or their existing code, drop it into the platform, and scale it up with a single line of code without any changes to their existing implementation, or very little changes. And so that just blows their mind, because they're able to go from processing, let's say, a week worth of data, if it's like a time series data, to a full year worth of data. And that's still at the experimentation stage. So they're no longer limited by infrastructure or by the ability to scale code. They're limited really by what they choose to use, or how much data they want to consume, as opposed to what their infrastructure allows them to. And so once they've passed that stage, once a scientist has successfully demonstrated that their solution works, even at a large scale, they want to deploy their work. And within Hyperplane, they can do that very quickly, simply by committing their Jupyter notebooks or Python scripts into a Git repository. Hyperplane takes a GitOps approach to managing scientific code. And so the way you deploy code is you just simply commit it to Git, and the rest of the platform is live synced with the Git repository and will pick it up instantaneously. There is no need to create any Docker files. There's no need to re-implement the notebooks as Python modules. Everything works as is, so you can take experimental code and deploy it and run it in an automated fashion, in a repeatable fashion, which you'll see in a moment when Will and Christine show you a demo. And so once the code is deployed, The next thing you want to be able to do is resolve issues, because as we all know, while notebooks are great and scientists love to use notebooks, generally speaking, the code that kind of ends up in Jupyter notebooks is usually not, it's usually not engineered for production. It's not architected for production. It tends to be scientific, and kind of the production readiness varies. Let me put it this way, right? So some people write great code. Some other scientists have less of a coding experience, and so the code is not great, but it does what they expect it to do in the experimentation setting. But now they've deployed it, it runs automatically, and it breaks. So what happens then? And so we've created the tooling around being able to fully reproduce failures back in the development environment, back in the Jupyter environment within seconds, fix and redeploy. And so the outcome is that scientists are able to become the operators of their own work. And they become essentially a self-contained unit that can experiment, implement, deploy, and maintain everything about their kind of machine learning solutions. And downstream teams, so other engineering teams, other DevOps teams, can consume that work by interacting with the APIs that Hyperplane exposes, which you'll see in a few minutes. And so this achieves a few things. It makes data scientists self-sufficient, but it also bridges the communication gaps that typically exist between engineering teams and science teams. So let's kind of look a bit more specifically at what is actually different when you start using Hyperplane. So the very first thing, as I mentioned, the very first thing that scientists notice is how easy it is to scale. We've integrated with the best distributed computing frameworks that exist. So the top ones we support are Dask, Spark, and Ray. And so these are all great frameworks. I mean, Spark has been around for a long time. Dask is an emerging framework, which is essentially pandas, has a similar API to pandas, but scaled up to infinite size data. And so we've integrated with all these frameworks, and we've made it extremely easy to set up a cluster of Spark nodes or Dask nodes that is fully networked, fully configured, has all the necessary packaging and permissioning, and can be used within a Jupyter notebook with a single line of code. So all the infrastructure work underneath happens with that single line of code. That also is, and we'll get back to it during the demo, the reason we took this approach is we think of clusters as ephemeral infrastructure. So rather than setting up a Dask cluster that exists forever and everybody uses and kind of competes for resources and needs to constantly be tweaked in terms of the configuration, we actually, the approach we take is make it extremely easy to spin up a short-lived Dask or Spark cluster that is configured for the purpose of a single task. So a single scientist performing one task or running a single experiment can spin up a Dask cluster that's configured exactly to perform that task with the right number of nodes, the right memory and CPU, GPU balance, run the calculation and tear down the cluster. And so this has many benefits. The most obvious one is the convenience. You don't need to interact with IT teams or infrastructure teams to kind of get a cluster that does what you need. You can just do it yourself as a scientist, and it's one line of code. The other benefits are isolation. So you have full isolation between notebooks, between users, between jobs. Each has its own cluster, virtualized, of course, and there's no conflicts of resources or conflicts of multiple jobs stepping on each other. And so that's the very first thing that people that use our platform notice and benefit from. The second thing is usually there's any data science project that starts as a Jupyter notebook has a phase where it goes through a re-implementation as a Python module that gets containerized or packaged up in some other way. And so we've entirely eliminated that step, and we've created the workflow and the mechanism to deploy Jupyter notebooks and other types of, I guess, regular scripts as well, but notebooks in particular, directly, right? So the way you deploy a notebook, you commit it to a Git repository, and then our platform will pick it up and you can run it programmatically, which we'll show you in the demo. And so this eliminates the need to create any containers and writing any Docker files writing any Python files, really. You can just take your notebooks, parameterize them, which we'll show, and then run them as pipelines or services. We've implemented mechanisms for automatic retries, both at a high level, kind of at a job level, and at a low task level. And what that allows us to do is to enable our users to use Spot infrastructure reliably. And so I think most of us will be familiar with the concept of Spot instances on AWS or preemptible instances on Google Cloud. Those can be 80% cheaper than kind of a persistent instance. And when you're performing large amounts of computation, so when, let's say, you're processing 20 terabytes of data every 5 minutes, you have a lot of infrastructure up to do that. And you can, of course, spin it up very easily through Hyperplane. But another benefit that Hyperplane provides is, by default, it will use Spot infrastructure for the worker nodes, which means you incur a significant amount of infrastructure savings. I see someone's having connection troubles. Can Emil, do you know what's going on with that? Can the rest of the group hear me?
I can.
All right. I'll keep going. Okay, so I'll keep going. Hopefully we can get Lou back into the presentation. Awesome. Thanks for confirming. So kind of going back to the Spot infrastructure, we automatically run the worker nodes for Dask or Spark on Spot infrastructure. And if any of that gets taken away by the cloud provider, we will restart a new node, scale up a new node, and rerun the calculation that failed. And so for any jobs or any workloads that can incur a few minutes delay, which is the time it takes to scale up new infrastructure, you can achieve very significant cost savings. It's really up to around 80%, or probably a bit less, because it's not always 80%, but it's very significant. You can go from hundreds of thousands to tens of thousands of dollars for the same calculations. And so integration. So one thing I haven't mentioned yet is DevSentient's philosophy and mindset is no vendor lock-in. We've suffered through vendor lock-in ourselves in our past kind of lives, and it's painful. And I think every practitioner knows that no one likes to have to do a lot of work before they see any benefit from a new tool, right? So nobody likes to do migration work. Everyone wants to kind of get to the point and start delivering, start solving. And so Hyperplane is built with that in mind. You can deploy it within an hour or two, and within existing infrastructure, no changes required. As long as the infrastructure can run a Kubernetes cluster, Hyperplane can deploy. And then you can take your existing notebooks and run it within Hyperplane with absolutely no changes. Where kind of the users of our platform start benefiting from the functionality that the platform provides is gradually, as they introduce scaling, as they introduce automation. Those are all things that are very minimal. So we try to compress as much as we can into a single line of code or a single API call. And that's to reduce the need to change, or remove actually the need to change any existing code or to change how you do your work. And then the maintainability. So one thing we'll show you during the demo is what happens when you're running your jobs in production and one of the jobs fails. So if you have an actual production job today without Hyperplane and it breaks at 2 a.m., who wakes up? So usually it's the DevOps engineers or the on-call that gets woken up. But if it's the model that's broken, you need the scientists to help. If there's no way for the scientists to reproduce the failure, they can't help. And so that leads to something which is not talked about a lot, because most data science POCs never make it to production. But one of the major issues with the machine learning solutions that do eventually make it to production is that it's difficult to have an effective process for maintaining them. Because if a job fails, you need to wake up both the scientist and the engineer, and the scientist needs to be part of the process. And so what Hyperplane provides is a very easy way to achieve two things. One is for the scientists to be able to reproduce the failures within their Jupyter environment, so they can, within seconds, literally get any notebook that failed in production with the embedded output and any errors that happen, run it, reproduce the failure exactly as it happened, and fix and redeploy by simply committing it to Git. Right. So this cycle of reproducing the failure, fixing and redeploying is extremely quick, because all you need to do is copy a reference, pull it into your Jupyter environment, fix how long it takes to fix the error obviously is situation dependent, but if it's something quick like a typo, it's an instant fix, you commit it to Git and you're done. And so the round trip can be under 2 minutes, right, for an actual production fix. And the other convenient thing is we make it very easy for DevOps teams to reference a specific job and a specific failure that occurred in production. So rather than having to explain extensively to a science team what happened, where it happened, and why, all an on-call needs to do is pass a reference and say, hey, this job broke, go fix it. And the scientists know exactly how to do that. And so the end result is that we allow our clients and we help our clients to go from idea to production in a few days, even in cases where previously it was kind of taking many months of struggle to kind of move things forward and take an idea forward. With Hyperplane, you can do it very quickly and in a matter of literally days, if not hours, for simple use cases. So with that, I will wrap up and hand it over to Will, who will show you a few examples of using Hyperplane. Will, are you on?
Yep. Thank
Awesome.
you, Evgeny. All right, just give me a second here, and I'll get my screen.
I'm going to
set
try
up.
to figure out how to stop sharing my screen.
Okay, I think I can take over from you.
Okay.
All right, so I'm going to walk through a demo of the Hyperplane platform and how to get up and running with a couple of different jobs on Hyperplane, specifically around spinning up a DAS cluster and working with GPUs. So this is the Hyperplane login screen. We support a variety of different types of single sign-on providers. Right now in this deployment, we have Google set up, so I'm going to log in with my Google credentials here. And the first thing that you'll see is the Hyperplane overview page. And I'll walk through a number of the features here. The first thing here up in the top is the Jupyter server. So this is pretty familiar to data scientists and other users that have used Jupyter Lab or Jupyter Hub. Secondly, we have the GraphQL playground. So GraphQL is a different type of API. It's different than REST, although it's a little more user-friendly in my opinion. And the GraphQL playground allows you to build up API calls for specific jobs or specific pipelines and invoke those pipelines or jobs programmatically. Thirdly, we have Grafana integration. So you can see various different metrics related to CPU, memory, network bandwidth, even the logs from your jobs or pipelines. And then lastly, MLflow integration as well. So you can set up experiments and you can log metrics and all the other fun things that come with using MLflow. And finally, down here at the bottom is just sort of a recent overview of what's happening on the Hyperplane platform. We can see a number of different jobs and we can toggle through their status. So let's go through a general workflow of what a data scientist would do here on the Hyperplane platform. Usually when they log in, the first thing that they're going to want to do is go to their Jupyter server. And you'll notice here that there are a number of different options. So these are images that at DevSentient we've pre-built to handle a number of different common data science use cases so that you can get up and running relatively quickly. We have our stable image here. So this contains a number of different common data science libraries and other Python packages. We have a deep learning image that is tailored towards deep learning workloads. So it has PyTorch, MXNet, transformers, those types of packages. One of our clients works with climate-related data. So we built an image that is tailored towards them and has client-related packages for them to work with. We have our GPU image, which comes with GPU support and GPU accelerated libraries like NVIDIA Rapids and GPU support for libraries like PyTorch. And then two other images here related to running things like SAS or R on Jupyter. And so I'm going to select the GPU image here. And what this is going to do is it's going to spin up a Jupyter Hub server. And we'll see in a couple moments the standard Jupyter Lab interface that most of the data scientists or your users of Jupyter Notebooks or Jupyter Labs are familiar with. All right. Okay, so here we go. Over here on the left, we have a user-mounted file system. So this allows the user to store local files or clone and interact with Git repositories. And then over here on the right is the main interface here, where I have a couple notebooks up that I'm going to run through. So this first notebook that I'll run through is just an example of how to spin up a Dask cluster on Hyperplane, and specifically how to work with GPUs on Dask. So I'm going to go ahead and import some standard packages. One of them here is our Hyperplane Python package, and this contains a number of different utilities to get up and running relatively quickly. One of them is our initialize cluster function. So this is going to handle setting up a Dask cluster. It's going to handle the networking, the security, all that stuff on the back end, so that as a data scientist, you can get working as soon as this is spun up. And you'll see here that there are a number of different options for you to specify, from number of processes, threads, memory, number of workers, number of GPUs, even where you want the scheduler to sit. A little more on the actual scheduler deploy mode. It can be local, it can be remote. With Dask, if you're running some large workloads, since Dask is lazily computed and maintains a computation graph of the operations, with large workloads, these can get pretty large and use up quite a bit of memory. So we have the option here of offloading that scheduler to a different pod. And we'll see here that Hyperplane also exposes the Dask dashboard that, if you're familiar with Dask, is a good tool to use. And you'll see if we go to the GPU tab here, we have a GPU attached, and it's used a little bit of memory. Okay, and one other quick thing I'll just reiterate. This is something that Yevgeny mentioned, is this philosophy around ephemeral clusters or short-lived clusters that are specifically tailored to a job. And by having this spun up in this notebook here, this allows you to tailor the cluster towards your job, have workload isolation by having it run solely on that cluster, and then you can tear that cluster down at the end of the job as well to make sure that you're keeping within your infrastructure span. So I'll walk through this example here. I'm just going to import the Dask distributed library so I can interact with the cluster. And my next step here will be to import the Dask cuDF library. So if you're familiar with using Dask, and specifically the Dask data frame, DaskQDF is the NVIDIA Rapids version of the Dask data frame. So allows you to run operations on a Dask cluster, but specifically on the GPU. So I'm going to load in some flight data here, and you'll see that I'm reading this in using the DaskQDF API, which is very similar to the Dask data frame API. And I'm just going to call head here to show the first couple of rows. We switch over to our Dask dashboard. You'll see, okay, we're consuming some memory as we're loading that data set in now. There was some GPU utilization over here a moment ago. Okay. And then I'm just going to run some quick operations here. So I'm going to run a group by, and I want to know for each carrier or airline and a given flight number, what's the average distance that this flight number completes. So we'll call that operation. And since Dask is lazily executed, we have to execute a compute. And I'll switch back over to our Dask dashboard. So you can see here, once again, we have some GPU utilization, GPU memory is being used up, and we can switch over to the task tab and see the task stream as well. Okay, and we have our results here. You also notice here that there's a cluster.close. So this will tear down the cluster at the end of the job. However, not to worry, if you forget to include this or if you forget to execute it, we have some smart garbage collection put in place so that if we notice your job finishes or your Jupyter Hub kernel is torn down, then we will garbage collect your cluster so you're not spending additional money on resources that you're not using. I'll switch over to my second demo here, which is going to be, once again, on how to easily use things like GPUs on Hyperplane. When it comes to using GPU accelerated libraries, oftentimes there's a lot of setup involved, and we've done a lot of abstractions to make this really easy to get up and running. Even when it comes to pulling down the Docker containers with those GPU accelerated libraries, they are relatively big and can be slow to pull down. And so we've done a number of different optimizations to make sure that there's a great user experience when working with some of these larger libraries. So I'm going to import those standard libraries again. And you'll see here, I'm actually going to read in some crypto trading data. So I'm reading in some Bitcoin data here. And I'm going to run something called TSNE. So TSNE is a dimensionality reduction technique, and it's particularly well suited to visualizing high dimensional data sets. I'm not going to run it on the CPU, otherwise we'll be sitting here for forever. And I'll just show you how fast it runs on the GPU. And so I'll quickly run that here. I'll walk through that. That should take about 20 or 30 seconds or so. If I scroll up just quickly, you will notice I actually used the pandas library to read in this Parquet file. If I wanted to speed this up, since I am doing an operation using Rapids, I could read this directly into the GPU instead of first reading it into the CPU and then copying it over to the GPU. So that's one way you could even speed this up. And if we scroll down, we see this done. It took about 20 seconds. And here's the visualization of the data set using TSNE. And so this is great, but what if I don't want to walk through this manually? What if I want a way of running this more programmatically or on a schedule or with various different parameters? How do I go about doing that? maybe, for example, I don't want to look at just Bitcoin, but I want an output for other different types of cryptocurrency. So we can run this on Hyperplane using a job or a pipeline. And the first thing to do is we create a YAML file. So I'll go over here to this tab, and this is just a simple YAML file that outlines my pipeline. So I give it a name, job type. This is a GPU related job, so it's going to run on that GPU image. And tasks here, which are just a list of the steps in the pipeline. And in this pipeline, there's only one step. You'll notice here I have my notebook path, and I also have a notebook output path. So in Hyperplane, we save the fully executed notebook, and this allows for easy debugging as well as increased auditability. And I'll show you those features shortly. So once we have that the YAML file, I'll switch over back to the notebook quickly, and I'll show you how we go about parameterizing this notebook. So as I mentioned, maybe I want to run this notebook with a different crypto. So right now I have the symbol variable in the cell. It's set to the Bitcoin symbol, but I can actually make this what's called a parameter cell. And the way I do that is by going over here to this little gear icon and making sure this cell has a tag called parameters. And if that's the case, then I can programmatically override this variable here. And I'll show you how that's done. So I'll switch back quickly to the Hyperplane overview, and I'll go over here to the jobs tab, and I'm going to create a new job. And so you'll see over here, excuse me, there's a number of fields that I can set, and you'll see here, these options are populated based on common fields that have been set in previous jobs. So I know this is a GPU related job. There's some timeout related parameters and max retries as well with respect to, if there's failures, how do I want to retry? And then my pipeline path as well. You'll notice here over on the left that there is actually a GraphQL query that gets populated. So if you didn't run this through the UI, you could do this programmatically using a GraphQL client, or hand this to downstream engineering teams to integrate this to the product. And then I mentioned parameterizing that notebook. Over here is where you add your parameters. So one of the parameters was symbol, and as value, I'm going to add Bitcoin. So I know that I have Bitcoin data stored in my Google Cloud storage. So I'm going to run this, and it's going to complete. But I'll run a second job as well. And in that second job, so you'll see now here, this first job is pending. In this second job, I'll put the same parameters, but I'll put a different symbol. So maybe I want to run this, on Dogecoin. And I don't actually have Dogecoin data in my bucket, so this is going to fail. But we can see how the debugging workflow looks like on Hyperplane. So I'll create that job there, and you'll see now they're both pending. Now they're both in progress, and when they finish for whatever reason, whether it be completed successfully or failed or whatever the reason, you'll see here an output notebooks path, and we'll be able to pull down that folder and see what exactly happened in the output notebook. So that's going to run. It's probably going to take 1 or 2 minutes or so. I'm actually going to go and grab the notebook from the previous demo I gave later this morning. So it's right here. You can see very similar details. I'm running that TS&E Rapids pipeline. And the symbol that I'm putting in is Doge. So let's actually go ahead and see what the actual error was. So I can easily copy over that output path, go back into my Jupyter Lab, open up a terminal here, and I can copy that down. So this is stored in my Google Cloud, and I'll bring that down. Okay, great. And so I'll go ahead and I'll open that up. And we see, okay, here is the fully executed notebook. Let's see exactly what happened. There was an exception thrown somewhere. We'll scroll down. Okay, it looks like I don't actually have Dogecoin data in my bucket as expected. And that's the reason why the pipeline failed. And so that's pretty much it for me in terms of a brief overview of the Hyperplane platform and how to really easily get up and running with the Dask cluster and with GPUs on Hyperplane. I'm going to turn it over to Christine, who is going to go through how to run a service using the Hyperplane platform.
Okay, thanks, Will. I think we might be out of time, but I just wanted to briefly talk about the services in which they're quite similar to how we would deploy a regular notebook. So maybe I'll go through just an example of what it could look like, and then we won't go into too much of the details. All right, so back in our Jupyter Hub environment, I just wanted to show what it's like if you wanted to actually run a notebook end-to-end without a specific end time or a timeout. So for this, we just have our crypto. For this, we have our crypto bot. Let's say we have this notebook that runs from beginning to end, and the last cell, as I wait for this to load, and the last cell is actually something, or one of the cells is actually something that we want to run an infinite loop and just keep this going. So of course we can just run this on our Hyperplane JHub instance, but another way to do this is actually to launch it as a pipeline job that never times out and launch it as a service that way. So to do that, first, we would create our YAML file like before and step, just the notebook similar to the notebooks from before. And then we go to our dashboard, and similar to the actual jobs, we just create a new service. But you'll see here that the timeout is already set to -1. So that's the only that's the main difference between when you want to run a never-ending job as a service. It's just that you go to the services page and you get a -1 timeout. And then, of course, as before, you can just specify your pipeline YAML path and then put some parameters. File, let's see. Yep. And then you can sort of create a service that way. And the second thing is, if you, let's say, don't have a notebook, but rather you have an application like a Flask app or a Fast API, like any other framework you want, right? Let's say we have an application that we'd actually want to run from beginning to end. And of course, we don't want it to time out, right? Because it's supposed to be like a live dashboard. So similarly, we just create our YAML file with the instructions on how to actually get that application up and running. So, pip install, and then you can also, it's really this line. So we just commit that like before, our YAML like before, and then we can then go back to our services page and then create another service. And the only difference here is because we want to actually expose that URL on the front end, we would then put an expose port, which tells Hyperplane, okay, first don't time this out, and then also expose this port. And then you, of course, can add your parameters as normal. And this will create, at this point, we already have our Hyperplane crypto bot running, and we also have that dashboard running. So like the jobs, Hyperplane will sort of pick those up and auto scale the infrastructure to get those jobs up and running. So I would also like to show, so once you have an exposed port, it actually comes, or something like this will pop up where we have a sort of dashboard link. And then as you can see, this is a dashboard with the app.py that we had earlier. So when you specify an exposed port, you can actually also see the dashboard that you just built. And for ours, it's just updating with some of the prices and some of the sell events. So yeah, I think at this point, we want to save some time for if there are any other questions. So Chizuram, I hope this also answers your question about the pip as well, just a little bit. If you just had a couple of things that you wanted to add, like for example, pip install Flask. I mean, we actually do have an image with like dashboard specific packages. So those are already built in, but let's say you wanted to add something on the fly, you can also just pip install. It's probably better if you specify a version. So if there are any other questions, please feel free to put them down here. I think our contact information is also here, so please feel free. Let us know if you have any questions about DevSentient or Hyperplane or other, I guess, usage or technical questions as well. I think we're at time. Yeah, and Emil, is this, all right, thanks. I guess, Will, did you want to wrap up or add anything?
Yeah, so just on behalf of everyone at DevSentient, thanks for joining us today. Please don't hesitate to reach out if you have any questions or comments. We'd be glad to speak with you, and enjoy the rest of MLOps world.
Okay, thanks all.